We will continue with the 11th lecture in the course on process control, analysis, design and assessment. So, we have been talking about analyzing transfer function models, and in the last few lectures I have been talking about getting time function out of Laplace function. And remember, we talked about an input that comes in gets converted to a Laplace domain function, gets multiplied by the transfer function, and you get an output Laplace domain function, which could be anything. We could call it y of s, and basically what we want to do is, while we have the result in the Laplace domain, we want to still get the result back in time domain, because that is what makes physical sense. So, how do I go from y of s to y of t? Here we are using g of s to g of t. And remember, we also said that if I do a Laplace of input, that is going to be some numerator by denominator function, and then I have the transfer function, which is also a numerator by denominator. So, any output is also going to be a numerator by a denominator polynomial, which is of this form right here. So, as long as the denominator polynomial is of a greater order than the numerator polynomial, we are looking at coming up with one general method using which we can do this inversion. Once we know how to do this inversion, we do not have to really worry about what the actual forms are. We can always get a solution in time domain. So, ultimately we are looking at getting a g of t, which is Laplace inverse a numerator by denominator. And one technique which will always work as long as you have this form is this partial fraction. So, there are no cases where you can say I cannot do partial fractions. You can always do partial fractions with this notion that the denominator is a higher order polynomial. And an important thing to note that is that once you have these polynomials could have real or complex roots. So, you do not want a technique which only works for real roots or complex roots and so on. Actually, what we are going to show, it does not really matter whether it is a real root or a complex root, it will always work, and that is the reason why we are going to use the notation p as a pole of a transfer function. So, whatever I am deriving here and whatever result I am showing here, you can simply follow that result whether the root is complex or real, it really does not matter. The only thing that will happen when you have complex roots, there will be a complex conjugate root pair whenever you have a complex root, that is the only thing. And basically when you have a complex root and a complex conjugate pair, you think of them as two roots of the system and then simply proceed the way that I am going to show you in terms of how you should do it. So, let us start and then say I have L inverse of n over n of s or d of s. Now, let us keep the numerator polynomial the same, but the denominator polynomial I am going to write in what I am going to term as root resolved form, which basically says that there is an nth order polynomial here. So, we are generalizing this now, and this nth order polynomial has, let us say, r roots. If no root is repeated, then it will have n roots, but if there are certain roots repeated, then it has r roots. Let us say that p1, p2, p3 and so on up to pr are the r roots, and let us also generalize this and then say the root p1 is repeated k1 times, the root p2 is repeated k2 times, and the root pr is repeated kr times and so on. Then the denominator polynomial, you can always write it as s minus p1 power k1 times s minus p2 power k2 and so on, s minus pr power kr. So, the condition is that since I cannot have more than n roots for an nth order polynomial, the condition is that n equal to k1 plus k2 all the way up to kr. Now, what we are going to do is we are going to repeatedly apply just one row of the Laplace inversion table, which is this. So, whenever I have a term of the form 1 by s minus pi to the power r, the Laplace inverse of this Laplace domain function is the following time domain function, which is t r minus 1, if this is r minus 1, e power pi times t divided by r minus 1 factorial. So, very simple formula. So, if it is 2 for example, then 1 by s minus pi squared will be t to the power 2 minus 1, which is just t, e power pi t divided by 2 minus 1 factorial will be 1. So, it will simply be t e power pi t. Now, let me illustrate this with, let us say, a denominator polynomial. let us assume it is of this form here, where there are two roots P1 and P2. The first root is repeated 4 times and the second root is repeated 2 times. So, that basically says that this is a 6th order polynomial, which then can be written in this form, which is s minus p 1 to the power 4 times s minus p2 squared, if we make the leading term as 1. Now, any ns by ds, okay, can be expanded if ds is of this form like this. So, in partial fractions, whenever some root is repeated, what you do is you add a term for every repeat. So, this is repeated 4 times. So, I have the first term, which is C11 by s minus p1, the second term is C12 s minus p1 squared, C13 s minus p1 cube, C14 s minus p1 to the power 4. So, the notation I have used is the first number here is the number of the root, this is the first root, and the second number is the time it repeats, right. So, the second repeat will be C12, third repeat will be C13 and so on, and correspondingly the denominator will be the corresponding powers, which is s minus p1 squared, s minus p1 cube and so on. And similarly, since P2 has repeated twice, there will be only 2 terms corresponding to P2. I have C21 s minus P2 to the power 1. So, 2 is this is the second root, the first repeat, which is s minus P2, second root, second repeat, s minus P2 squared. Now, you might wonder what happened to ns, does it not matter? Of course, ns matters, and what ns is would then define what these constants are. So, once you put the correct constants, you can know that by taking the denominator multiplication, you can simplify the numerator and that will turn out to be ns. So, I am going to show you how to compute this C11, C12, C13, C14, C21, C22 for general problems, but as of now this is a procedure, right. If someone told you how to compute the C's, then you have quickly inverted this Laplace domain function and all you need is just this, there is nothing else that you need. So, Laplace inverse ns by ds is Laplace inverse of this large number of terms, and using the linearity property of Laplace transforms, we can do Laplace inverse of this sum of 6 terms is the sum of 6 Laplace inverse terms. So, this will be Laplace inverse C11 by s minus p1 to the power 1. So, this is inversion of this with r equal to 1. If r is 1, this is going to be t to the power 1 minus 1 t to the power 0 is 1. So, it will have simply be e power p1 t C11 by 0 factorial. The second term will be using this C12 t e power p1 t by 1 factorial, and the third term is C13 t squared e power p1 t by 2 factorial and so on. So, what has happened is that this Laplace domain function has been converted to a time domain function, and the only thing that we still do not know is how to compute the constants, but otherwise the procedure is set, and irrespective of whatever functional form you get ns over ds, you can always do this partial fraction expansion. We will for now just assume that the order of the ds polynomial is greater than the order of the ns polynomial, and just to reiterate, the constants basically, if you compute them correctly, will help you retrieve n of s. However, the denominator terms, right, dictate really how many terms in the expansion you have. So, in this case it is a 6th order polynomial and there will be 6 terms. The 6th order polynomial could be in different ways. Here I have P1 repeated 4 times, P2 repeated 2 times. So, there are 4 P1 related terms and 2 P2 related terms. If for example, this d of s where s minus P1 cube times s minus P2 cube, then there will be 3 terms related to P1 and 3 terms related to P2 and so on. If all of them are non-repeated roots, then you will correspondingly have 6 terms, every one term will represent one pole or one root. So, if I have let us say something where the root is not repeated, okay, then how do I compute the coefficient corresponding to that? So, the idea is the following. So, supposing I have let us say ns by ds, and let us say this ds has one pole which is not repeated. So, basically this is going to be ns divided by some d1s times s minus pi, okay, this is not repeated. Then remember, when you do the partial fractions, there will be several terms which will all be functions of the poles other than pi, and then I will have this term which is s minus pi, okay. So, this is my ns by ds. So, we do not have to even expand this, I am just showing you that there will be n, if the order is n of this polynomial, there will be n minus 1 terms here, right, whichever way they are organized depending on how many roots are repeated or not repeated in D1s and so on. Now, a neat trick that you can do to compute the Ci is the following. So, what you can do is you can multiply this ns by ds, right, by s minus pi. So, if you multiply both sides by s minus pi, so ns by ds times s minus pi, if you do this, then this whole term where there is no denominator with s minus pi, because that I have separated it out, which is this here, will be multiplied by s minus pi, plus when I multiply this by s minus pi and s minus pi get cancelled. So, I have Ci. So, this will be the equivalent representation. When I multiply this, this will be equal to this. Now, notice something interesting. So, this is g of s times s minus pi. Now, if I set s equal to pi, so that basically means this is g of s minus pi. Okay. If I set this with s equal to pi, then what will happen on the right hand side is I will have this term and I will have pi minus pi plus Ci, because already the s minus pi while I did this we had removed. Now, this term will go to 0, then you will get the Ci is simply this. So, if I have a non repeated root, I do not need to do anything at all. To get the corresponding Ci for the non repeated root, I take the ns by ds or the gs function and I multiply that by s minus pi and then set s equal to pi and evaluate this, and this will give me Ci. Okay. So, this is for a non repeated root. If I have repeated roots, then basically it is not only one indicator, this is Cij, where we said I refers to the root number and j refers to the repeat for which we are writing the term. So, if there is a root I which is repeated thrice, so Ci1 will be s minus pi power 1, Ci2 will be s minus pi power 2, Ci3 will be s minus pi power 3 and so on. So, this Cij can be computed using differentiation, and the differentiation formula is this. So, what you do is assume that this root ith root is repeated ki, right. So, that is a notation we had used in the previous slide, where we said P1 is repeated k1 times, P2 is repeated k2 times, P3 is repeated k3 times and so on. So, ith root will be repeated ki times. So, this is you do this differentiation d ki, the number of times this root is repeated, minus j, whatever jth coefficient you want, divided by ds ki minus j, and inside you have this gs times s minus pi power ki. So, here we multiplied only by s minus pi because it is a non repeated root. For repeated roots we have s minus pi power ki times gs, okay, and then you evaluate this whole thing at s equal to pi, that will give you the constant Cij. So, this way for every I you can compute all the j's. Now, this ki minus j, let us say if it turns out to be 2, then basically this will be d squared by ds squared. You have to differentiate this gs times this 2 times. If this ki minus j turns out to be 3 for a particular j, then that is d cube by ds cube. Basically, you have to differentiate this 3 times. Okay. Now, this is a simple formula that you can use, which will give you all the c's that we saw in the previous slide, and then that will basically allow you to invert any n of s over d of s very easily. Now, this might look a little confusing because of this k minus j, what is this d squared, ds squared and so on. We will look at an example and work this out in the next slide, so that you get a very good idea of how this is done. And once you understand this, understand how this is done, now you are empowered to do all kinds of inversion. You do not have to look at any other table, albeit I should warn you that when the roots are complex you can still use it, but the calculations will become very tedious. So, there are tricks that people use, there are tricks that are used in books to do quick Laplace inversion. So, you can learn those tricks and then do Laplace inversion much faster than this laborious process. Nonetheless, this laborious process will never fail you. So, if you are ready to do the work, this will give you the inversion every time. More importantly, another reason actually to really focus on this in this lecture is the following. So, if you look at this, I am showing you a procedure to compute the C's, but irrespective of that it is either going to be a real or a complex constant, right. So, ultimately I can simply leave this as C11, C12 and so on for understanding in terms of stability and other issues with respect to control. So, what this partial fraction idea does for us is it gives us a conceptual framework to understand how this inversion is done. Then that will tell you how you can really think about stability of these control systems, performance and so on. So, you will see the power of this notion of partial fractions later as I teach stability in very simple fashion, because once you understand this, then the notions of stability becomes almost readily apparent. So, we really do not have to worry about these constants to understand stability. However, if you want to actually invert this and then do some computations and so on, of course, you need to calculate these constants and see how they come about. So, the point is that whenever you have complex coefficients you can still do it, but let us say if one complex root is repeated twice, then correspondingly the complex conjugate root also has to repeat twice. So, for example, if P1 is a complex root and I say it is repeating twice, then because of the way the math works, the complex conjugate root will also have to repeat twice, and basically you will think of this as one root repeated twice, this one as another root repeated twice, because they are not the same roots, P1 and P star are different. Now, let us take a very simple example and then see how this inversion process works. So, let us take this example, g of s is 1 over s squared times s plus 2. If you just notice in this case the root s equal to 0 repeats twice or occurs twice, and s equal to minus 2 occurs only once. Okay. So, now you start with this and I want to invert this, then the idea is quite simple. We know it is a third order polynomial and there are 3 roots 0, 0, minus 2, and since 0 repeats twice there will be 2 terms corresponding to the root 0 and then there will be 1 term corresponding to the root minus 2. So, Laplace inverse 1 over s squared times s plus 2 will be Laplace inverse C11 s. So, notice the notation C12 s squared. So, this is the first root and the first term, this is the first root second term and this has s squared, and this is the second root first term s plus 2, and there are no more terms because it is a non-repeating value. Now, for the 2 repeated roots C1j, we said d k I k1, in this case since s equal to 0 repeat twice, that k1 is 2. So, d 2 minus j, ds 2 minus j, this is gs times s minus pi to the power ki. So, this is s minus 0 and it is repeating twice, so s squared. So, I am going to say 1 by s squared times s plus 2 times s squared, and differential of this and set s equal to 0, it should give you the 2 roots. So, this is what we have. Now, when we want C11, that means j is 1. Okay. So, 2 minus 1 is 1. 2 minus 1 is 1. So, this is d by ds, and s squared gets cancelled, 1 over s plus 2. Okay. So, when I have this, so d by ds of 1 by s plus 2 will be minus 1 by s plus 2 whole square. So, this I have to evaluate at s equal to 0. So, when I set s equal to 0, this will be minus 1 by 2 squared equals minus 1 by 4. So, which is what I have here. When I want C12, I substitute j equal to 2. So, this is d 2 minus 2 is 0, ds 2 minus 2 is 0. So, there is no differentiation, it is simply 1 over s plus 2 evaluated at s equal to 0. So, I put s equal to 0, this is half. For C21, since it is not repeated at all I need to do is I have to multiply gs by s plus 2 and substitute s equal to minus 2, the roots value. So, when I do that, s plus 2 and s plus 2 get cancelled, I have 1 over s squared, and when I put s equal to minus 2, I get 1 by 4. Look at how simply we are able to do this computation. So, once I have these, then I can put this C11 as minus 1 by 4. So, this is minus 1 by 4 s, C12 is half and this is s squared. So, half s squared, and C21 is 1 over 4 s plus 2, and when we do this Laplace inverse using the other formula that we have, this is going to be minus 1 by 4 plus t by 2 plus e power minus 2 t by 4. So, it is a very simple Laplace inversion using just that one row of the table that I showed in this slide and in the Laplace table. So, you can see how this is getting inverted into this using this partial fraction idea. Now, this idea is very general, as I said, and you can use this on any ratio of polynomials when the denominator polynomial order is greater than the numerator polynomial order. So, which is an assumption we are going to make as far as this course is concerned to do this partial fraction expansion. And as I said before, irrespective of what n of s d of s is, you can always use this approach, but you can see if I have, let us say, complex roots and so on, then many of these will become complex numbers. However, when you put all of those complex numbers in and do the expansion, the imaginary part will automatically vanish, because the Laplace inverse of this has to be a real function, because we are working with real systems. So, that will happen, the mathematics behind this will make sure or ensure that no imaginary part is left behind. So, when you combine all of this, the imaginary part will go to 0. So, if you are doing this expansion, actually if there is an imaginary term that comes in, you can simply ignore this and then do the other terms, because when you collect all the imaginary terms together, they are anyway going to go to 0. So, you can get the real part of the answer, which will be the answer for your inversion. Okay. So, I hope this gives you a good idea of how this Laplace transform inversion is done, and we will pick up from here in the next lecture. Thank you.